So, good morning. We continue with our discussions on the solutions of the homogeneous linear systems with constant coefficients. Now, we have taken up details of a simple scenario, namely the assuming the matrix A is the constant coefficients is diagonalizable with only real eigenvalues. So this is all fully loaded. I mean, the statement is fully loaded. There are things like we are assuming that there are only real eigenvalues. I am not assuming that all the eigenvalues are the the eigenvalues, each eigenvalue is of multiplicity 1. That is not what I am assuming. But what I assume is that it gives you enough eigenvectors to construct a basis for a Rn. Okay, so that with respect to that basis, certainly the A is diagonalizable with diagonal elements lambda 1, lambda 2, etc., lambda k. Each lambda I repeated as many times as the multiplicity of the algebraic multiplicity of lambda as a solution of the characteristic polynomial. Now, polynomial equation, that is p lambda equal to 0. Yeah. So that's the assumption that we have made. So we assumed A is diagonalizable with real eigenvalues, and in that scenario we worked out what will be the general solution. We also considered some examples. Now, at that time I said, let us for the time being postpone the possibility of complex eigenvalues. That is something that we have not considered yet. Now, remember the class of n by n matrices with real entries having all the eigenvalues real is not not a small class. This, for instance, I said that when we consider symmetric A, namely Aij equal to Aj, then one can easily prove that all the eigenvalues are real. Okay, that is, there are no non-real eigenvalues at all for this problem, and that's a huge class. And that's not only a huge class, it's also one of the very prominent class of matrices that are of interest from the point of view of application. Okay. So it's not a small class that we have considered, but certainly a very simple scenario. Now we assume diagonalizability, but allowing A to have complex eigenvalues also. So that is the next thing that we are considering. So complex eigenvalues. Assume, okay, the equation we consider is dx by dt equal to AX, where A is equal to Aij. And also we consider, so we denote this by 1, where AIJs are real. However, see that A may have complex eigenvalues also. This depends on the zeros of the polynomial, because the eigenvalues are or what we call characteristic. The zeros of the characteristic polynomial say P lambda of E. Okay, now P has real coefficients. Which implies if lambda belonging to C is an eigenvalue A0 of P, then lambda conjugate is also an eigenvalue further. If Ax equal to lambda x, x non-trivial and complex value, then Ax conjugate lambda conjugate x conjugate. Therefore, lambda conjugate is an eigenvalue A with x conjugate as an eigenvalue. Remember, this is valid only when A is assumed. That is, this is valid because Aij's otherwise you cannot make this statement, because what happens is complex conjugation will come, and then x bar will be an eigenvector belonging to an eigenvalue lambda bar of a bar, which may be a different matrix. Okay. Okay, right. I mean, that's quite easy to see. Therefore, you see that if lambda is an eigenvalue of A, lambda bar is also an eigenvalue of A. Therefore, the eigenvalues, complex eigenvalues of A appear in conjugate pairs. Okay? Right? And that's something that we have. And so also about the eigenvector. Now we observe the following. Suppose xt of the x. Now you know how you make this solution. You start with a vector which is not equal to 0. Use that as a initial value, and then write down the corresponding x. Okay, so such solutions exist. Existence is no problem at all, and this may be complex, and if x eigenvector of A belonging to lambda not necessarily real, then corresponding xt, we also have this dx by dt equal to ax for the corresponding xt. Corresponding eigenvector and xt is an eigenvector of A belonging to lambda for each t. That means you have this property that A so this is something that we have seen, and they are complex. Okay, so it's a solution of the homogeneous equation. Now we observe that, so we have seen that X. In that we have seen how you work with it. Use the fact that X is a complex solution, satisfies this, etc. Then what you do is you take the real and imaginary parts. So you get equate the real and imaginary parts. You get two equations, and both real xt and imaginary xt are also two real solutions of this one. So now assume are the distinct eigenvalues of when we are not assuming lambda i's then what you have, let mk be the mi be the multiplicity of lambda I. Then what you can do is that there exists linearly independent vectors x one m1. Okay, let me write ni n1 are eigenvectors A, each xij being the eigenvector, an eigenvector belonging to lambda I for I equal to. So this is what we have. So this forms a basis for Cn in fact. Okay, and then you have the corresponding solutions. So we have the corresponding complex solutions. The corresponding complex solutions are of 1 are, that is 1 is this one, dx by dt equal to ax, are these functions are there. and they are complex solutions of the equation which are linearly independent. Then we have R2 real valued solutions of dx by dt dx. Okay. So from among all solutions with I equal to 1 k j equal to I equal to k. I mean, sum of the may be 0. If xij is a real solution, then it is going to be 0. So there may be real eigenvalues also. For instance, if you take 3 by 3 case, okay, then what happens? The polynomial, the characteristic polynomial is of degree 3, and being a polynomial with real coefficients, you see that in C you have all the 3 zeros, but you know that the complex zeros appear in conjugate pairs. Therefore, certainly one of the roots of P are going to be real. Okay, the other two may be a multiple real root, or it could be even a sort of you know, in conjugate pairs. Okay, so all roots are distinct, and the two of them are the complex roots are appearing in pairs. So, okay, so this is the scenario. So you will get at most 2n linear 2n real valued solutions of this equation, out of which precisely n of them are that's quite easy to see. Work it out for each T naught. Then what you have, xij t naught is in general a complex vector. Okay. Now that complex vector has a real part and an imaginary part in general. I mean, maybe some of them may be real also. So you get corresponding to this as many real vectors as possible. Now you see that real xijt is a solution of dx by dt equal to ax, subject to the initial condition that real xijt equal to real xij t naught at t equal to t naught, one of the given vectors. Okay. Now you see that these real vectors form a basis for Rn, right? That is the evaluation of this form vectors in Rn, and Rn, the dimension of Rn is n. Therefore, a basis can be obtained from this. Why a basis can be obtained from this? The reason is this. Suppose you look at the evaluation of all these vectors at t naught, a point t naught, some point t naught on the t interval. Now what happens? You have n linearly independent complex vectors. From the diagonalizability, it follows that you have a basis consisting of these eigenvectors for C. Okay, for the solution space. Now you take the real part and then you have got now a class of real valued solutions of the equation. And does it take care of a fundamental, does it give you a fundamental basis or a fundamental set of solutions for the differential equation? Now this is the question that you have. Okay. Now you can see that this actually does. Why it is so? Because you look at the corresponding vectors. Okay. So the question reduces to whether the corresponding evaluation of these vectors give you n linearly independent vectors. Suppose it doesn't give a basis for Rn, then what happens? And assume that n minus 1 of these vectors can span the entire Rn. That is what can happen. Okay. Suppose n minus 1 vectors of this type can span Rn. Then what happens? Every vector xij t naught can be written as a linear combination of those n minus 1 vectors. Okay. So it really so how we have chosen these vectors? The initial conditions have been chosen such that the initial values are all the vectors are all linearly independent. So that's a contradiction. So it's not the span of these complex vectors cannot be the span of the real vectors. So there's a problem that each one of these real complex vectors can now be written as a linear combination of these vectors with I also coming into the coefficients. Okay. So that's a problem. So therefore, from this we are able to get a fundamental set of solutions. Okay. So that's one important aspect. Let us look at an example. Take the very simple example. Now you see that in this case A is equal to and what you call the eigenvalues of A are non-real, because you see that determinant of and the roots are, and these roots are given by what are these? I n minus I. Where I is equal to imaginary unit. What are the eigenvectors? The corresponding eigenvectors is, okay, let us compute the eigenvector for is the following. What do you have? We have to write A so we have to choose A minus I of x equal to 0, which will give you two equations, which implies minus I equal to 0. Okay. You see that these are the two equations where now solve these equations. So now these equations have a multitude of solutions, because this is the coefficient matrix is not invertible anymore. Therefore, what are the, so one such solution, by picking up, giving one value for x1 and the other one you can write as x2. So x2 equal to, one solution is that, okay, x we can take as, set x1 is equal to 1, then x2 equal to x2 equal to minus 1. And as I said earlier, that x conjugate, what is x conjugate? Is then equal to 1i. okay, is an eigenvector minus. This is quite easy to check. Okay. Therefore, what are the solutions that you have? So xt equal to what is it? 1 I e to the power it is one solution. So x1t we take as this, and x2t is are two linearly independent complex solutions. X. So they span the whole space. So what are the real solutions? The corresponding real solutions, let us take. So real part of x1 this is equal to, what is the real part of x1? It is 1, 0, e to the power it is, so this is equal to real part of 1 minus I cos t plus I sin t. Let us write down the real part of this. What is this? This is the vector given by, first take this one, so you get cos t, then the other part will come from here, cos t sin t. Okay, and imaginary part of this is equal to sin t cos t. Now these are two real solutions of the differential equation, because what is the differential equation? The differential equation is this: 1 by dt equal to minus x2 dx2 by dt. Now you check with this. Suppose you take x1 equal to cos t and x2 equal to sin t, and you see that dx2 by dt equal to x1, dx1 by dt is equal to minus x2. So also you take these two, take x1 equal to sin t, then x2 equal to minus cos t, then you see that cos t equal to minus of minus cos t. So this satisfies these equations. So these are two real, so these, and similarly you can get the same thing from working with x2. Working with x2 also, okay. So you get two linearly independent solutions. and they are linearly independent. And hence a fundamental system of solutions so that's what you get. So you see that this is how you get a fundamental set of solutions for the problem. Now you can do the same thing for higher order equations and so on. So whenever you get a complex eigenvalue, then from that you can construct a basis consisting of real functions. So that is the complex case. So complex case is handled exactly as you did in the other case. Same theory applies, and then you can immediately write down what is called a real basis for the solution space, or a fundamental set of solutions from which a general solution is a linear combination of these solutions. I want to make a remark. Now these are not eigenvectors of A. They are not eigenvectors of A. Okay, right? Because this equation, this A has only non-real eigenvectors. So they are not eigenvectors of A. That's for sure. Okay. So now we will take the general case. Now we begin with the general case. Where we are now dropping the assumption that A is diagonalizable. Now we drop that assumption. And what do you end up with? Therefore, we don't have any more the eigenvectors of A this is one problem. Okay. Now the question that you are asking is, how do we proceed in this particular case? Okay, it's a bit complicated, but probably worthwhile to see. Now I'll give you an example where this happens. So we start with an example. So we begin with this example. Take up this example. So we take A equal to three, 1, minus 1, 2, 2 minus 1, minus 1, and 2, 2, 0, 0. And we have the equation dx by dt. Now excess So as before, observe that equal to is the characteristic of A, that is determinant of therefore the roots are lambda equal to 1 of multiplicity one and lambda equal to 2 of multiplicity So lambda is equal to 1 is an eigenvalue of multiplicity 1 and lambda equal to 2 is a eigenvalue of multiplicity 1. Lambda equal to 1 does not give any problem, and one observes that one zero two. So null space of I is equal to the span of the vector 1 0. So that's it, and hence e to the power what is it? It's equal to 1. So T of now we want to get in fact 3 such vectors functions. Let us start working with 2. We hope we will get 2 such linearly independent vectors. Now let us see what happens. You see that the A minus 2I, easily compute, what is this? This is equal to minus 1, 2, 0, minus 1, and the other one is 2, 2, minus 2. Now what about the rank of this? The rank of A minus 2I is equal to 2. It means the nullity of dimension of the null space of A minus 2I is equal to 1. This is the problem. Okay. So you see that you don't get 2 linearly independent solutions, 2 linearly independent vectors which form eigenvectors of 2. You get only 1. So this gives certainly, so we can easily work out what that solution is. That is quite easy to see, because all that you do is you take, you have 2 equations, x1 plus x2 minus x3 equal to 0, and 2x1 minus x3 equal to 0. So let us take x1 equal to 1. If you do that, then you get x1 equal to 1. Then that puts x3 equal to 2. x1 equal to 1, x3 equal to 2. So you get 1 minus 2, so x2 equal to 2. 1, 2. And quickly check whether it is true. 1, 2, no. Okay. What is that you have? x1 is equal to 1, so x3 equal to 2. Right. So let me fill in this rightly, correctly. Okay. One. Okay. 1 minus 2. So x2 equal to 2. Now it is right. So this satisfies this one, and this also satisfies this. Okay. So this is a vector. It's a non-zero vector. It is linearly independent of 1, 0, 2, which spans a one-dimensional vector space. Okay. So you see that you get, what you get is 1, 0, 2. Is a basis for, is span of this is not equal to R3. This is the problem. Therefore, you need to construct another vector, and once you get another vector, you can get another solution. And that, in this case, it is easy to pick one vector which will does the job, but we want to pick a something that is very characteristic to this equation. We will go about doing that. So that's our job. Now I will stop this example at the moment here and then return to it. Okay, so let me just start with the further analysis of this will be taken up later. Okay, right. So let us start with the general theory. What is our strategy? Let me just give you the strategy. The strategy is start with a vector in Rn, then solve the initial value problem. Dx by dt is equal to Ax. Subject to that initial condition, you will get a solution. Okay. So if we start with n linearly independent vectors of Rn, then you get n corresponding solutions, and of course the added complication may be there may be complex eigenvalues, etc. So it doesn't matter. I mean, So we try to find out this. When you build a general theory, you need some framework. For an individual problem, it is not difficult to handle. Okay. So let us start working out a general theory for this problem. So let us start with the general case now. So the equation is Ax. Now A is equal to Aij. So x we take as xn and xt we take as so we consider characteristic values of A. These are roots of the characteristic polynomial. Of A. What we have is that, let us assume that lambda 1, lambda 2, etc., lambda k distinct roots of the characteristic equation of A. assume lambda I is of multiplicity mi for I equal to that is this is what you have. It's from the general theory. We are not assuming this is diagonalizable. That means the eigenspaces or the null spaces of A minus lambda I will give you sufficiently many vectors to span Rn. Now this is the problem that you encounter. In that case, how do you proceed? So we have to start. So we work with what are called primitive solutions of one. Which are what are the primitive solutions? Which are the ones corresponding to the vectors of A associated with the characteristic values. The characteristic values of A. So we show that starting from vectors associated with the characteristic values one can a fundamental set of solutions So let us start with the notation. Now, let me just explain what is the problem. If you have sufficiently many eigenvectors, linearly independent eigenvectors, which amounts to saying that you take one particular lambda I. The algebraic multiplicity of lambda I is mi. So the algebraic multiplicity of mi. What about the dimension of a minus lambda I? The null space of a minus lambda I. See, this may not be mi, or it could be, or maybe strictly less than mi. Then what you see is the problem is this: if you cannot break up Rn to be the direct sum of 1 to k of the null space of this may not be equal. This is the problem, because you see that each one of these subspace of Rn, and this is a direct sum, they are linearly independent, so it's a direct sum, etc. So you won't get as many vectors as required to span this. So we have to bring in some additional vectors. Okay, so that's the problem. Okay, so how to get hold of these vectors? What one does is this. See, you look at this one. Lambda I equal to 0. You can show that this is equal to 0. Okay. Therefore, what we do is that you want to find out vectors which satisfy these equations, and they may not be a minus lambda I x equal to 0, may not be of the form. So there may be some vectors of that kind, but not all. Okay. But if you can certainly get vectors of this class, which will span this whole space. Okay. So if you choose vectors satisfying these, then you can certainly construct mi linearly independent vectors which will span the null space of a minus lambda I. Okay, so that's the problem. That's the problem that we have had in that example. In that example, 2 is an eigenvalue of multiplicity 2, and you got only one eigenvector which spans it. If we had 2, then I think we would have been through, but that is not the case. Okay, so how to get hold of that? So you have to work with this one, a minus 2I solutions of this. You know that if a particular x satisfies the condition a minus 2I x equal to 0, then certainly it satisfies this requirement. But there exist vectors which are not necessarily satisfying the condition that many linearly independent does not exist sufficiently many linearly independent vectors in R3 such that this is equal to 0. That's a problem. Therefore, how to supplement it? How do we choose such vectors? This is the question. Yeah, very simple example, but we have to give a theory which gives a very systematic way in which you can get hold of these vectors. Once you get that, then corresponding to those vectors, you solve the equation, because you are assured the existence and uniqueness theory tells you that with those vectors as initial data or initial condition, you have uniquely determined solutions of the equation. Okay, and those solutions will serve you as a fundamental set of solutions. Now, this is the strategy that we are going to make, exactly as we did in the diagonalizable case. So, let us start with the notations. I think this we have said denoted by T for convenience. This is the equation that we have considered. So this, let me designate this by 2. If P is any polynomial with constant coefficients, then PD of x, this is equal to PA of x whenever dx by dt, that is dx ax. So whenever x is a solution of this equation, then you see that PD of x is equal to PA of x. Now this is very easy to work out, okay, right? So you take PD and operate on this, apply d by dt equal to ax, then you get the polynomial emerging here, and this is what you get, and that's very simple to verify. Therefore, what we prove is that if xt is a solution of 1, and we also observe one more thing, if xt is a solution of 1, then x derivative of t is also a solution of 1. This we have already seen, because that is quite easy to prove. I think we have proved it earlier. All that you are assuming this is true. Now you take the second derivative, or you take the derivative of this. So you see, d by dt of A is a constant matrix, therefore you see that if this relation is true, namely x is a solution of this equation, then dx by dt is also a solution of that. You just replace, see, if I write dx by dt as y, then dy by dt equal to a y. So y is a solution of 1. So more generally, if P is any polynomial More generally, P is any polynomial, then PD of X one whenever X is a so this shows that dx is a solution of 1. Therefore, d square x is a solution of 1. D to the power kx is a solution of 1 for any k, and then you take the linear combination because the problem is homogeneous linear. You see that PD of x is a linear combination of powers of d acting over x. Therefore, that's also a solution of 1. That's quite easy to see. Now, this is an observation that we make, which we are going to make use of. So, we have the following theorem. Let xt be a solution of the equation 1. Suppose some t naught of t xt naught is a vector associated with a characteristic value A with multiplicity m that is a minus lambda I m equal to 0. See, xt naught, if it is an eigenvector of A belonging to the eigenvalue lambda, then this equation is certainly satisfied. But there exists other vectors which satisfy this particular equation, okay, for M. And those vectors are all called the vectors associated with a characteristic value lambda of A with the multiplicity M. Okay, so this condition is satisfied. Then the same relation is true for all values of t that is, you have A minus lambda I and also d minus lambda I This condition let me denote by 4, and then this I denote by 3. This condition I denote by 3, and this, okay. Now let us prove this theorem. The proof is very simple. So you observe the following. Observe that a minus lambda I to the power m xt is identically equal to d minus x, provided of course x is a solution of the equation, provided okay, so that is true. So let z you define as then because xt is a solution of 1, you see that any relation of this kind, its derivative is a solution of 1. In fact, any polynomial in D acting over x is a solution of 1, and therefore in particular zt is a solution of 1. That is simple. A linear combination of its derivatives. Now you see zt naught is what? Zt naught is equal to, see the same thing evaluated at, this is equal to a minus lambda I t naught. Because d minus lambda I to the power m xt is the same as this one. That's the reason. Okay. Therefore, implies, and we are taking an xt naught such that this is equal to 0. Okay. So we take zt naught equal to 0. We are taking a solution, a vector which exists of this. Okay, so xt naught we take as in this way, and that is the corresponding solution that we are looking at as it is given here. Okay, this implies the corresponding solution zt is identically equal to 0. because you have this equation. And see how ZT naught is chosen. It is chosen with xt naught. Xt naught is considered as a solution of the equation a minus lambda I to the power m xt naught equal to 0. Okay. So for such a thing, this is true. That is, we have these two relations, d minus lambda a minus lambda I equal to 0. This is what we have proved. Now, so this theorem shows that there exists solutions of this kind. Of course, it hangs on this, that you can find out an xt naught such that zt naught equal to 0, and therefore you see that zt identically equal to 0, which means the d minus lambda to the power n xt identically equal to 0, and this is also identically equal to 0. Okay, but xt may not be equal to 0. Xt is not equal to 0. For instance, if you work with eigenvectors, it does work. But there are vectors other than eigenvectors which also satisfy this condition. So let me now define So let me make a definition of what is called a primitive solution. And once we define that, I think I'll leave it there and then take it up in my next lecture. So we define what is called a primitive solution. A primitive solution associated with the characteristic value lambda of multiplicity m is any non-trivial solution of one for which there exists a characteristic value lambda of A and a positive integer m such that This is what you call a primitive solution. So the solutions constructed out of eigenvectors are all primitive solutions associated with the corresponding eigenvalue. But there may be other functions which do the same, have the same, this particular property, which may not be eigenvectors at all. So we will just give the interpretation of the theorem. The theorem we have proved above says that xt is a solution of one if and only if there exists some T naught of T such that xt naught is a vector associated with the characteristic value lambda of multiplicity So the process is this: lambda is a eigenvector or a characteristic vector of multiplicity m. Then you choose a vector associated with the characteristic value lambda of multiplicity m. That is what a vector of the form a minus lambda I to the power m x t naught equal to 0. Okay. Now for that vector you construct the solution xt, and then zt equal to d minus lambda to the power m xt is identically equal to 0. A minus lambda I to the power m xt is identically equal to 0. So what we can prove is that this corresponding xt is a primitive solution of 1. Okay, that's the theorem. That is what the theorem says. So such solutions exist because it is supported by the existence and uniqueness theorem. Now we are going to work with this primitive set of solutions, no more the eigen vectors and the corresponding solutions, but a wider class of functions which are associated with this, which gives you sufficiently many functions to construct a fundamental set of solutions of the equation. Okay. Thank you very much. Let me stop here and then continue with how we actually compute such solutions in a specific case. That will be the theme that we pursue in the next lecture. Thank you very much.